This year.
We're going to stay for
4 years to see us forward.
to get us.
I will say that as actually.
The final question.
So that is our assignment sheet. I really made it kind of easy. I'm really shocked we have this many people here. This is crazy.
Thank you.
I'm pretty sure you will.
Yeah, the person.
And I can see that even for your. I'm going to kind of take it easy on you if you had a rough time getting in the swing of things at home. And that I'm not going to teach you anything new today, which is kind of unprecedented. I really didn't know we didn't even know what we were going to do this week until late Friday. So, or whether we'd be here or not. So what I'm going to do is go back through what we were doing with that Gaussian elimination, because that's always a tough spot for a lot of people. Please make sure you understand this well, because we actually are going to have it on a test, on our next test on matrices, because the whole idea of Gaussian elimination is worked into matrices, but we're going to be doing more a calculator approach to things, but the mentality is still going to have to be there. So I could call this Gaussian elimination. We might call it elementary row operations. Eventually, we're going to call it reduced row echelon form. There's all kinds of different ways to talk about what Gauss did. Also, have y'all seen the movie Look Up?
Yeah.
I didn't watch it. Have you seen it? I saw it last night. He actually referred to Gauss in there when he was doing his calculations to figure out where the thing was going to hit, and they figured out it was hitting Earth, whatever. Nice. But yeah, then he referred to Gauss, and I was like, nice. Anyway,
Was it good? Was the movie good?
it was good. Definitely worth watching, and really shockingly relevant to how ignorant our world is in a lot of ways. So anyway, here's what we're going to do today. If you did struggle with that at all, or if you haven't watched those videos, I would encourage you to go back and look through them. But we're just going to talk today. If you feel really comfortable with it, there are some homework problems on that sheet. If you want to just start working on those, you can. But if you don't, I'm going to do a couple of problems just to remind you about where we are and what you would do in a situation like this. So what we're looking at is solving systems. So, and by the way, you can use this process with any system of equations, even with a very simple one, like we've been doing it with the elimination method for a while with just like linear systems with X and Y. The one we were looking at, I guess Friday, was X, Y, and Z. So even though the book might call them linear systems, they're really planes. So let's just say we had a system like 2x minus 3y plus c. I'm just making something up here. And let's go with hold on. Trying to make it work out nicely. Hold it. Okay, let me double check this. Okay, so I believe our answer is going to be 1, 2, -2 for your x, y, z, I think. So we're going to get a system like this, and our goal was to solve using that Gaussian elimination. So we said what our hope was, and we talked about this in our video, what our hope was to magically turn this into a system where there would be no x term there, and there would be no x term there, and there would be no y term there. So basically, these three things would be gone. Now, obviously, in that process, the coefficients of this y and z, these values are going to change because we're going to be doing linear combinations, essentially. But if those go away, all you'll have left is one variable here, which will be really easy to solve for, right? Like if you just had something like -3z = 9, you could solve and get z as -3. So granted, that 3 is going to change. But we get that solved, and once you have that variable, you can back substitute it or substitute it back into this equation. And again, if that doesn't have an x term, you plug the z in there and solve for y. And then once you have that y and that z, you plug them both back in here, and that will eliminate everything but the x, and you can solve for x. So that's our goal. But how do we go about doing that in a situation like this is our question that we have. So what we're going to do is essentially do linear combinations to get rid of these three values right here. So the rules that we gave you for those reducer echelon form process, the Gaussian elimination, what were the rules that I said that you are allowed to do? And I wrote those out. Anybody watch the video?
Switch the order.
Okay, so if you want to change the order to begin, knock yourself out. So if you're like, you know what, I kind of wish that x, y, -3z, 9 were on top. Obviously, it's just three equations, right? The order in which I give you the equations doesn't matter. So if you decide you like having a 1x on top just because it makes your calculations better, great. Do that initially, and at any point you can switch those up. Or like, what if I gave you a problem that had a missing, say this one did not have an x term. And you're like, well, I really don't want it set up that way. I kind of want to have an x term right there. Well, if you wanted, you could take this one, put it on top, and you could take this bottom one, which is already missing that term, and leave it in the second row because you would have already had x eliminated. And I kind of forgot what my x was. Was it 2? 2. Okay, and that's supposed to be the z right. All right, so I want that there. I want to make the 4 go away. So I can change the order. What were the other two things? I can add or subtract. You can combine by addition or subtraction or whatever. What do we say? Any multiple of these, any two equations. So if I want to, and that also essentially means the third one, which was I'm allowed to multiply by any non-zero number. Obviously, multiplying by 0 is not going to be helpful, but any non-zero number I can multiply by. So right here, if I wanted to say make that 4x go away, and I wanted to use this top equation, what would I need to do with that top equation so that I could add it to the second equation, right? I can multiply by -2. So I'm going to multiply that by -2, and then I'm going to add those together, and I have the right to replace either of them with the result. And we actually talked a little bit about this in Algebra 2 when we dealt with matrices, and we were talking about how to simplify them. You could always combine any two rows together and replace one of them with result. That was Gaussian elimination, essentially. So I'm going to go ahead and multiply by a -2 right here, which would give me a -4x, right? Wait, I'm going to use a different color. That gives me a -4x, a +6y, a -2z, and a +12. And I'm going to be using that in place of this, right? And I'm going to add it to the second row. And what would that give me? 0. So if I want to put a 0, I can, or I can just leave it blank. 7y, or +7y, -4z, and finally 22. And if I want, I can now copy the original equation over, or I could copy the red equation. It doesn't matter. If you like keeping your numbers smaller and you don't think you're going to need -4 again and 2x would be fine, you're welcome to bring over that yellow equation. I don't really need that red one. I've already used it, so I'm going to kind of ignore it now. Although on your test, show your work as much as possible. And then rather than copy the bottom equation and the top equation down and then start the process again, I'm going to knock out 2 steps. I'm going to make this x go away. What do I need to do to make that x go away? I can multiply the bottom one by -2 and combine it with the top. So if I did that, I would have a -2x, -2y, +6z, and a -18. And I'm going to combine that top equation with that new third equation, which would give me 0x. I don't have to put a 0, but it's going to hold that place. -5y, +7z, and -24. And at this point, I'm going to just bring the top equation over. So I usually, in one step, or it's 2 steps actually, but in one equation, I make that a 0 and that a 0, and then just carry back over the 2x minus 3y plus z equals -6. And again, if you wanted to use that top red equation, you could, but I have now made those 2 values 0, and those are 2 of the 3 places that I want to have zeros, right? Now I got to basically get rid of the y. At this point, it looks a whole lot like the linear combination you've been doing for a while, where, okay, I need to try to get rid of this y term, so I'm going to multiply the top by a 5 and the bottom by a 7 and add them together, and the y's will go away. That's essentially what I'm doing, but we're going to show this form. We're not just going to be all over the place when we solve, because on this test, I want to see this process. So I'll literally in the problem show, I'll be giving you an example and say, I want you to solve, and I want these 3 to be zeros, so it's really clear to me you know what you're doing. So in the next step, what could I do to make that value a 0? So I'm going to multiply the top by 5, which would give me 35y minus 20z equals 110. And the bottom by 7 would give me -35y, positive 49z equals what? -168. And then I'm going to combine those 2 yellow equations together, but I'm going to keep the top equation again. I'm going to bring it over here. I'm going to keep 2x minus 3y plus z equals -6. I'm going to keep that second. I'm going to keep the red one because the numbers are smaller, right? Why not? Or if you said, well, how can you do that? Well, remember, you're allowed to multiply. Well, I could now turn around and multiply that yellow one by a 1/7. And I'm back to what I had in the red, which is 7y minus 4z equals 22. And then when I add these 2 together, I get another 0, which gets rid of the y spot. I get a 29z. And at this point, I'm going to know if I've made a mistake. A -58. And when you're doing these at home, I can't promise you on the homework questions, although you have the key, you can look at your answers. But if you get really terrible fractions, like when you're doing this on your test, if you get z equals 49/27 or whatever, and it doesn't simplify, you've made a mistake. Because I'm going to make you have nice whole number answers. Okay, and I'm not going to give you credit for an answer alone. I'm going to need to see the process, but you will have confirmation, not whole number, but integral answers. Like this one is 1, 2, -2. And you can see right there when you solve for z now, when I set that and divide by 29, there's my -2. Once you have z, you're going to plug it back in there, and that gives you 7y minus 4 times a -2 equals 22. And when you take that 8 and subtract, you get your y value. And then once you get your y value, you're going to take your z and your y and plug it back in and solve. And you're going to get 2x, -8, or 2x equals 2, and x equals 4. And because we want to write these as nice, neat, ordered triples, we're going to write 1, 2, -2 as our solution. Not too bad? Okay. Yes. Yes. Yeah, so some of you, if y'all are board, you can just go whatever. The next problem I'm going to do, though, those are the ones that people tend to miss the most. Okay, so people tend to, if they miss this, it usually is a careless error and they can't find it. If that happens, by the way, if you get to here and you get z equals some weird fraction and you're like, what on earth? Just go back. You can see I've made a million calculations. You make one wrong calculation and you're going to get a terrible fraction. One sign error, you're probably going to get a terrible fraction, which is going to snowball on you and become worse and worse. So on that first value, if you get something ugly, just go back out. Some of the most frequent mistakes are copying the problem down wrong. That's not going to be an issue when you're taking your test because you're going to have it given to you. But just be really careful about signs, things like that. All right? Now, what happens when you are solving and you're going through this process, right? I'm just going to pick a different question. Okay, so what happens if during the process of you solving, this occurs? Say you end up with, and you go and you make this first one a 0, and then and you make this one a 0, and then the process of trying to make this a 0, you end up adding that stuff together, and this occurs. You get a 0 there and a 0 there, and then some random number here. What does that mean to you? It means that these three planes didn't all intersect in one or more places. So if that happens, and you know that 0 is not equal to 6, if something like that happens, you're going to just say null set and walk away, or no solution and walk away. That's great. Now, I would caution you to be careful, right? Make sure that you're checking your work and this didn't accidentally happen, right, through a mistake. But it'd be rare that would happen. But if you do get this correctly, and this is a false statement, you're going to say null set. All right, now, what happens if in this process, and this is the part that's trickier to people, what happens in this process if you're trying to get those two zeros, and then you go to make that a 0, and everything ends up becoming zeros in the denominator? What does that mean? That means you have infinitely many solutions, but you can't say infinitely many solutions. This would be an example of where like the planes intersected in a line, or maybe they were intersected in a plane. But if you have infinitely many solutions, you have to find a way to describe all of those solutions. Okay? The Z thing, the book uses A. I just don't bother going and substituting A back in for Z. But the point is, when this happens, what you're going to do is write your answer as basically a big ordered pair. But it's going to be like a formula. We're going to learn later that what we're really writing out is a system of parametric equations. And parametric equations describe, or they can describe, a pattern through space. So we're like an equation of a line just moves in a plane. If I want to move through space, I've got to basically have something that describes X, something that describes the Y, and something that describes the Z locations. So what I'm going to do is have a little formula that describes all the points that move through space. So what I do is I start with, well, whatever Z is, I'm just going to call it Z, and then describe the Y and the X in terms of Z. Now, if you watch what I'm doing the exact same thing I did before. But before, what did I do when I first solved for Z? I got my answer for Z and did what? Plugged it back into that equation and solved for Y. Well, I'm going to do the same thing, except what is Z? It's not a number, it's just a variable. So rather than taking the number and plug it in, I'm just going to say, all right, plug Z in, which it's already there, but take that and solve for Y. So you're kind of doing the same thing, except instead of having a number to plug in for Z, you're plugging the variable in, which is already there, and solving for Y. So what you end up getting here is 4 minus Z divided by 2. So your Y value, it's a little ugly, I'll give you that, but that goes here. And you could write that like that. You could write it like 2 minus a half Z. And then what would you do then once you had your your y and your z? You plug what? But prior, you would have plugged both of those here. We'll do that. Except this time, you're going to use this y value there. And of course, you're going to use z for z. And you're going to solve for x. So I get 2x minus 3 times this ugly new y value plus z equals 5. And you're going to solve for x in terms of z. So here, this gives you what? Minus, if I'm distributing that in, minus 12 halves, positive 3z over 2 plus z equals 5. So this is a little ugly. You're going to add that 6 to get an 11. You're going to subtract the 3z over 2, and you're going to divide everything by a 2. And dividing by a 2 just puts an extra 2 in the bottom there. So you either get 11 minus 3z, 11 halves minus 3z over 4, or if you want to write it as a fraction like this, you can, but either way, I'm just going to go 11 halves minus 3z over 4. And I usually make the answers here a little bit better looking than this one. Are you with me? Okay, that's probably one of the more missed questions, believe it or not. Hopefully it won't be this year because we're spending an extra day on this. Kind of let your feet dip in the pool a little bit after being gone for so long. The one thing you got to be careful about is sometimes I will not start you with 3 equations. All right, if I don't start you off with 3 equations at all, and I just say, and you don't get to this point, if I just start you off with 2 equations, you mentally can just go, oh, well, if I only have 2 equations, I can just pretend like there's zeros in there, make that a 0 right there, and start this process again. So what I'm saying is essentially this. I might have a situation where I just say solve. You'll see this tonight. Now we should know right now what happens when 2 planes, I ask you to solve for 2 planes. What are you going to get? One of 3 situations. They're either going to intersect in a line, they are going to not intersect at all because they're parallel. How would you know that they're parallel? What would they have to have? Think vectors.
Oh, you wrote vector, dot vector. I don't remember.
Well, that's true. There would be a dot product of 2 things that we're going to be looking at in 2 seconds. The dot product, the dot product would be 0 if they are perpendicular, but they would be parallel. So it would be the cross product would be the 0 vector. So but what am I looking at? It's not slope. I'm looking at these numbers. What are those? What do those coefficients make? Do you remember when we talked about an equation of a plane? What are those? If you have a plane, what does 1, -2, 1 represent? You don't remember? The normal vector? Remember in the equation of a plane? If you have a plane, the vector coming out of the plane is the normal vector. That's the 1, -2, 1. So if you look at that, and that, and that, and that, and you see the same thing or a scalar multiple of it, that means they share the same normal vectors. And if they have the same normal vectors, they're parallel. But clearly, these are not parallel, are they? Right? So if I don't see parallel normal vectors, or the coefficients aren't scalar multiples of each other, if I don't see that, I know I'm going to get an answer that's linear because the 2 planes are going to intersect. So what do I need to do to find that formula? I need what? I technically need zeros there, there, and there, right? Because that's what I do when I normally solve. Now, because I don't even have a 3rd equation, I've already got all of those zeros, right? So I really just need to make that a 0 right there. How would I do that? So maybe multiply the top by a -2 and add it to this, and I would keep the top equation the same. This now becomes a 0x, so there's a 0 there. an 8y, a negative 3z, and a negative 2. And isn't that kind of what I wanted? So I'm treating it just like I did before. I'm imagining that there's a third equation that's all zeros. And look, I've got my 3 zeros. I've got that confirmation that there's infinitely many solutions. And what would I do now to start the process? So I know that z is what? Z is z. And then now what do I do to solve for y? I kind of plug my z back in, which it's already there, and I solve for y. I didn't think through this one, so my answers are probably going to be terrible. So there is my y in terms of z. And then what do I do to find x? Plug both of those in here to solve for x. So I get x minus 2. Actually, this is not going to be too bad. Minus 2y plus the z equals 4. And that cancels. And I get x minus 3z over 4 plus 4 over 4, which is 1. Right? And that shouldn't be too bad. This and a 4z over 4 give me a 1/4 of a z. So I am going to move that 1 over and subtract a 1/4 of a z. And that would be my x coordinate. And again, I usually make these a little bit easier to deal with if it's a problem on your test. Y'all with me? So that is Gaussian elimination on a 3-variable system. Now, what do you think you do if you have x, y, z's, and w's? So hypothetically, what would you do if I had something like this? And we're not gonna solve this. What would I need here to be able to complete this process that I'm talking about?
You need to cancel out like the x in the second equation, the x, y, and 4.
So he's saying I would need a 0 there, a 0 and a 0 there, and then what?
0, 0.
A 0 there, there, and there. And at this point, we're really talking about a lot of tedious math. I'm not going to make you do that manually. If you are an engineer at a university and you have to take certain math classes, sometimes you have to take math electives. One of the easier math electives when I was back in the day was coding theory. And coding theory is a bunch of matrix applications. And they talk about, the nice part about it's all zeros and ones because it's all binary code. So the math is a little bit easier than all the big numbers. But the point is you do a lot with elementary row operations. At least you did in the 80s and 90s, so I don't know what you do now. But the point is, for each one of these, I would have to make these zeros again, because once they're all zeros, wouldn't it be really easy to solve for the W? And then to plug back in and solve for the Z, and then plug back in to solve for the Y, Z, W, and then et cetera, et cetera. So we could finally get there. What we're going to do is once we start getting to bigger systems like this, we're going to pull our calculators out. Our calculators have a little button that all I have to do is treat it like a matrix. I can basically type this in, assuming I actually remember the values there, but I can, what I could do is look at this thing like a giant matrix and just plug in the coefficients like 1, -2, 1, 1, 4. And I can hit this little button called reduced row echelon form. And it just magically turns this thing into a giant, looks like this. It's really awesome. And then you might have like random numbers here. So through this little button called reduced row echelon form, you'll REF this big giant coefficient matrix, and it spits this out. Well, if you think about it, if the big coefficient matrix, if the number there stood for X and the number there Y and the number there Z, this would be like giving you 1X plus 0y plus 0z plus 0w equals 2, well, what do you instantly know? X is 2. And this would be like 1x plus 1y plus 1z plus 1w equals 3. Well, what do you instantly know? Y equals 3. So in the next chapter, we'll do all that. We might still review this Gaussian stuff, but we'll do the stuff with our calculators. And there's another form that's called row echelon form. And row echelon form is not as good, but that's essentially what we're doing. Row echelon form just makes these numbers zeros here. And then these other numbers could be anything. I mean, it could be, I don't know, it could be anything, but it basically just gets rid of the zeros here. I mean, it gets rid of these numbers and makes them zeros and lets you back substitute. But we're not even going to do that because it's so much better to use reduced row echelon form because it just jumps straight to an answer, a matrix answer. Anyway, that's for another day. We feel okay about this? Okay, so if you already knew this stuff, great. Hopefully that'll be a good review. Got a couple homework problems for you to look at. Do your best on it, and then tomorrow we will jump into partial fraction decomposition. And for those of you that are thinking about taking BC calculus next year, it is a topic that you need to know how to do to integrate certain problems. If you plan on taking AB calculus, then you would not need that for an AB course. But if you go into any math and science field, you would need to have Cal 2. So most people that go into engineering fields are in my courses. There might be a couple out there that aren't, but most people are. So if you are in you're even thinking about a math and science field that would need Cal 2, that's what we're going to work on tomorrow. And we might even do it 2 days. I don't know what got into me, where I'm going to slow down like this. It's unprecedented. Yeah, I'm really taking it easy on you this week. I really was expecting it to be like, oh no, like I think we had 100 families in the system as of Thursday say that there was COVID running rampant. So I was trying to make it a little bit easy on. I was really expecting it to be like a shell of a class.
They tested, and the nurse practitioner there was like, yeah, we had like 40 kids come in, and they just wasn't negative.
Yeah. There's a lot of it going around, but it's pretty contagious. My family got it over the break, so I feel empowered. Breathe on me all you want. No. Breathe away and feel safe around me because I've already been infected and healed. All right, what's all that?